especially we are talking about interval estimations and hypothesis testing. Okay. Beware of testing too many hypotheses. The more you total the data, the more likely they are confessed, but confessions obtained under jurors might not be admissible in the court of scientific options. Okay. In previous lectures, we have discussed about the ordinary least square methods to estimate the parameters, and now we are going to estimate the interval estimations. Okay. Internal estimation, some basic ideas. To fix the ideas, consider the Wakes education example of chapter 3. We have question 361, so that the estimated average increase in min hourly wage related to 1 year increase in schooling. If schooling increased by one year, that's mean the wage increased by 0.7240, which is one number estimate of the unknown population value. How reliable is this estimate? It's noted in chapter 3 because of sampling fluctuations. A single estimate is likely to differ from true value, although its repeated sampling is mean value is repeated to be equal to the true value. Our objective is to estimate the sample regression model at least near to true value of the estimates. Okay. So therefore, instead of relying on the point estimate alone, we may construct an interval around the point estimator, say within 2 or 3 standard error or either sides of point estimator. Such as interval in our class, usually we use 95% probability, including the 2 parameter value. Okay, this is roughly the idea behind the interval estimation. Okay, to be more specific, assume that we want to find out how close our estimator to the true value. Here, for example, we try to find out 2 positive numbers of delta and alpha that are lying between 0 and 1, such that the probability that the random interval beta 2 hat minus delta and beta 2 hat plus delta. This is the ring between 2 coefficients contain the true value is 1 minus alpha. 1 minus alpha means the confidence interval level is 95%. This is the formula to calculate the interval estimations. Here, probability that this estimated parameters between beta 2 minus delta and beta 2 plus delta. This, we hope our estimated results between this the true value is between our estimated result. The parameter is small enough to make sure that our estimator is not biased. Such an interval, if exists, is known as confidence interval. Alpha minus 1, 1 minus alpha is known as the confidence coefficients. Alpha from 0 to 1 is now the level of significance. The endpoint of confidence interval are known the confidence limits. We have 2 limits here, lower limit and upper limit. Lower confidence limits, then upper confidence limits. In passing, note that in practice, alpha and 1 minus alpha are often expressed in percentage form as 100% and 100 times 1 minus alpha percent. Okay. Okay, after some derivations, we get the confidence interval. our estimates, our estimator. First, we use these distributions, student distributions, normal distributions. This is normal distributions. We use a normal assumption for residuals in our classical linear regression assumptions that residual are normally distributed. So because we have a normality assumption in residuals, that means the estimator also have normal distributions. So we use this equation 531 to represent the normal distributions. Okay, because we have a small samples, that means we have to use student t distributions. This is student t distribution. 532 is a student t distributions for small sample properties. Okay, and normal distribution is a large sample properties. Okay, if we use t distributions, we will get that if t goes to unlimited, the value of t is equal to normal distributions 1.96. Okay, suppose here I'll show you the t distribution there. This is t table. We have t distributions. Okay, yeah, we assume that we have 95% significant level. So we have here 1.96 here, 1.96. This is equal to normal distributions. That means if sample size increase, that means normal distribution is equal to student t distributions. So from the beginning equation, we can transpose the equation from normal distribution to student t distribution. So now we use equation 533 to estimate interval estimates. Okay, this t value is we get from t table. Okay, therefore, instead of using the normal distribution, we can use t distribution to establish a confidence interval for estimators, not only beta 2, also beta 1, and other betas. Where the t value is in the middle of this double inequality is the t value given by equations 532, and where t alpha over 2 is the value of t table obtained from t distributions. Okay, because we are using two-sided test, that means alpha is 2 parts in the left and in the right, so alpha is divided by 2. We substitute equations 532 into equation 533. We get the probability of interval estimations for the parameters is equal to equation 534. After rearranging the equation 534, we get the equation 535. This is a confidence interval. We use this equation to calculate the confidence interval. Equation 535 provide 100% confidence interval for beta 2, which can be written more compactly in short equations, such as in equation 536. So beta 2 plus minus t alpha of over 2 times by standard error of the parameters. So the equation here is the short term. First, we calculate the beta 2 and we take the t value from t table, distribution t. We multiply with standard error of the respective parameters. If we calculate for beta 1, that means here standard error of beta 1. If we calculate for beta 2, that means here standard error of beta 2. Okay. Arguing analogously, using equation 431 and 432, we can write this probability of the beta 1. Equation 536, this for beta 1 is actually is same as the equation 536 because the difference only the parameters and the standard error of the parameters. So in the compact equations, the confidence interval for beta 1 is beta 1 plus minus t alpha over 2 times standard error beta 1. Okay. This is for example. Okay, for example, returning to our regression example in chapter 3, section 36, mean hourly wages on educations. We found that beta 2 is equal to 724 and standard error of beta 2 is 0.07. Okay, because we have 13 observations, degree of freedom is 11. Because we have two cases here. K for the first K is beta 1, the second K is beta 2. This means degree of freedom is degree of freedom is equal to sample minus K. Okay, if we estimate the simple regression model, okay, that has two parameters, means the K is equal to 2. So degree of freedom is a sample size minus the K. Okay, if we estimate the multiple regression model, for example, we have the 4 independent variables. It means we have 5 parameters. Okay, that means K depend on the estimated equations. The more you have independent variables, the less the degree of freedom. So I mentioned already that you have to make sure that you have long enough sample size to guarantee that your equation, your estimate equations is more reliable. So I want to explain these coefficients. We get the beta here 0.724 and we have a standard error 0.07. So the critical value for degree of freedom is 11 is 2.20. Okay, I will show you these coefficients. Okay, here we have 95%. Sorry, 95%. This means we have 11 here. We get 2.201. Okay, we have samples 13 minus 2 parameters. That means degree of freedom is 11. Okay, because we said that the significant level is 95%. That means we have 2.201 for the critical value of this step on based on these equations. Okay, here we get 2.201. It is no need to memorize the table. Okay, no advantage to memorize this value, critical value of this distribution, T distribution. Okay, because we have here 2.20 and we have standard error 0.07. This means we multiply 0.07 by 2.201. This means we get 2.201 times 0.07 is equal to 0.15407 plus, okay, the coefficients, the estimated coefficient 724 equal to x7 x0, this one, 0.87 x07. Okay, if 0.72, let me write down here. We have the coefficient of the parameter, and we standard error is 0.07, and T value is 2.201. It's better to write down here in the whiteboard, virtual whiteboard here. Okay, I change the color here to make it more clear. Okay, we have betas. Beta 2 is equal to 0.724. We have standard error of beta 2 is equal to 0.7, and we have T critical value for degree of freedom is 11 is equal to 2.201. So the confidence interval, okay, we have here upper limit. We have upper limit here 0.724 plus 0 plus 2.201 times 0.07. Okay. Here we get the resource, or it is better to make it a blue color. Okay. We get here 0.87x07. Okay, now we calculate for lower limit. It's equal to 0.724 minus 2.201 times 0.07 is equal to, okay, here we get 2.201 times 0.7 is equal to 0.15407. This means 0.724 minus 0.15407. We get here 0.56993. So our confidence interval now, the lower limit is 0.56993 and 0.8781007. Okay. If we look at the estimated coefficient, is 0.7024, is between the confidence interval level, and there is no negative signs in the confidence interval. This means that our estimated coefficient is is close to the true value. Okay, you get it? So we have the beta 2 is 0.724, and the confidence interval lower limit is 0.56993, and the upper limit is 0.87807. This means the beta is lie between the lower limit and upper limit, and because we have positive beta and the confidence interval also positive sign, this means the estimated results, the estimated parameter is close to real or true value. You get it? Any question?
Yes, sir. What if you have a negative sign?
Okay. For example here. Okay, sorry. For example, for example, we have we have estimated coefficient is 0.534, and the confidence interval, confidence interval, we have confidence interval, the lower limit, for example, here minus 0.124, and upper limit we get 2.687. Okay, this means that our estimated parameter is not lied in the true value, because for example we estimate this is a consumption function. For example, we have this consumption function. Theoretically stated that if income increase, the consumption will increase, but because we get the confidence interval consists of negative signs, that means if income increase, then the consumption may be decreased. This is not a true value based on theory. You get it?
Yes, sir.
Okay. Any other questions? No question? No problem? No understand? No any question?
No, sir.
Okay. We continue our class. Okay. So this one for beta 1. Okay. Almost the same as beta 1. This one beta 1. Beta 1. Also, this one beta 1. We get the interval given a confidence interval by 2%. Table 3.2. Okay. Again, you should carefully in interpreting this confidence. Okay. Because you want there is a negative sign. Yeah. It is a negative. It's a good example for you. Okay. Okay. Confidence interval for sigma square. As pointed out in chapter 4, section 4.3, under the normal assumptions, the variable of this is a chi-square distributions. Okay. Actually, we have some distributions. Yeah. Okay. Normal distributions. We use Z here. Student T distribution. We have T distribution here. F distribution. And then we have chi-square distribution. Chi-square distribution. Okay, usually we use this these distributions. Okay. This is the graph of chi distributions. We have this one, the lower parts, this upper parts. Okay. Following the chi distributions with n-2 degree of freedom, therefore we can use chi distribution to establish confidence interval for sigma square. Okay, you can look at the equation here. The probability of chi distribution here, chi square with the 1 minus alpha, here 1 minus alpha over 2. Here. In the lower limit, we have 1, sorry, we thought the square, 1 minus alpha over 2. Another one here, upper limit is alpha over 2. This is different value. It's not the same as T distributions. Okay, that means we have two values of chi, so critical value in chi-square distributions. Okay. Okay, the chi-square value in the middle of this double inequality is given by equation 541, and where chi-square with 1 minus alpha over 2 and chi-square alpha over 2 are two values of critical value obtained from chi-square table for n-2 degree of freedom. Sorry. I will show you the chi-square here. Sorry. This is the table here. This is chi-square table. Okay. This shaded area is equal to alpha for chi-square. Is equal to chi-square alpha. If we have alpha by percent, we have here. This means another one minus alpha by percent over 2. This means 0.25% here. And we have another one here, 97.5%. Okay, we have two different values for the chi-square distributions. Okay, so be careful to use this critical value of chi-square distribution. Substituting chi-square from equation 541 into equation 542 and rearranging the terms, we obtain the equation 543. Here we have n minus 2 times sigma square hat over chi-square alpha over 2, and here we have n minus 2 chi-square over sigma square over chi-square 1 minus alpha over 2. Okay, with the same example from the table 3.2, we get the sigma square is 0.8936. We have chi-square here, 0.8936, and we choose alpha is 5%. Okay, for the chi-square with the degree of freedom of 11, give the critical values. Okay, for the chi-square 0.025 is equal to 21.92, and chi-square 97.5% is equal to 3.8157. Okay, I will show you this table. Okay, we have 11 degree of freedom. Here, we have 11 degree of freedom. Yeah. This is the critical value for 97.5%, and we have 21.92 for 2.5%. Okay, we have two different values. You get it?
Yes, sir.
Okay. Okay, now we calculate the values. Yeah. Okay. Okay, you can calculate by yourself. Here we have n minus 2, that's mean 11. Okay, we have sigma square is 0.8936, and we have okay, this mean 11 here times times 0.96 the 936 over 21.92. Okay. It's for confident interval for sigma square. Okay. We have here 11 times 0.8936 divided by 21.92 is equal to okay, let's calculate this one. 11 times 0.8936 is equal to 9 point something divided by 21.92 is equal to 0.4484. This is the lower limit, and then we get the upper limit and 0.8936 over 3.8157 is equal to okay, 11 times 0.8936 is equal to 9 point something divided by 3.8157. We get here 2.5761. Okay. Because we have here, this is the coefficient of sigma square. Okay. Sigma square coefficient is 0.8936, and the confidence interval we have 2 here. 0.4484 and 2.565761. Okay, this means we have good estimators because the value of chi-square is between these values. Any question? No question. Okay, if you don't have question, we continue on. Okay, what is the interpretation of the interval? If we establish 95% confidence limits on sigma square, and if we maintain a priori that these limits will include the true value of sigma square, we will be right in the long run 90% of the time. Hypothesis testing. Okay, we have two-type testing here. We have two-sided and one-sided. Okay, we have two-tail or two-sided testing, and we have one-sided, one-tail test. To illustrate the confidence interval approach, once again, we refer to our wages education example. From the regression results given in equation 361, we know that the slope coefficient is 0.724. Suppose we postulate that we assume that our objective is to test whether the beta 2 is equal to 0.5 or not. Okay, this is if you state that beta 2 is equal, for the null hypothesis, we said beta 2 is equal to 0.5. That means we have alternative hypothesis. This is a two-sided test. Okay, because we have two tails here from the negative to positive areas. The true slope coefficient is 0.5. This is a question. Is the true value is 0.5? And the null hypothesis, but less than or greater than 0.5 under the alternative hypothesis. The null hypothesis is simple hypothesis. Simple hypothesis. Whereas the alternative hypothesis is composite. Actually, it is on the two-sided hypothesis. This one here, in the left-hand side, is a rejection area of beta of hypothesis, null hypothesis. In the middle is the area of acceptance. Here, we have in the right-hand side, we have a rejection area of null hypothesis. Now, decision rule. I have explained before. We have two approaches. Okay, first, we have conventional approach, and the second one is modern approach. For the conventional approach, we compare the calculated statistic with the critical value. If the calculated value is greater than critical value, this means null hypothesis is rejected. Okay. Modern approach we use here, the value of probability to set null hypothesis by using p value. If p value is less than 0.05, this means we reject null hypothesis. I explained already for this rule. Okay, do you remember the rule? Okay, this is the rule, same rule. Okay, one-sided one-sided or one-tailed test. This, if we set here null hypothesis is less than, so the alternative hypothesis should be greater than, the opposite from the null hypothesis. Okay, I explained already in the beginning of our class, we have two testing, hypothesis testings. First is individual coefficients, and another one is a group coefficient. If we use t-test, this means we test for individual. Okay, this is the formula to calculate the t statistics. Okay, we have here beta 2. Beta 2 is estimated equations, beta 2 hat, and we have beta 2 is a true value, and also we have here standard error of beta 2. Okay, according to the probability here, okay, we have a confidence interval between the value of estimated value. Okay, we give the interval in which beta 2 will fall with 1 minus alpha probability, given beta 2 is equal to beta 2 star. In the language of hypothesis testing, the confidence interval established in equation 572 is now the region of acceptance of the null hypothesis, and the outside of region is a rejection area of null hypothesis. Okay, here, once again, let us return to our wage education example. We have here beta 2 is 0.724 and standard error is 0.07 and degree of freedom is 11. We have critical value of t distribution 2.201 and we want to test whether the beta 2 is equal to 0.5 or not. So we get here probability 0.346 and 0.654. Here we insert the value of beta here, estimated beta, and is we assume the true value is 0.5. We divide it by standard error of the beta. We get is 3.2. Because t value, t calculated value is greater than the critical value of 2.201, this means we reject the null hypothesis. So, okay, we notice here that if estimated beta 2 is equal to beta 2 hat, is hypothesized beta 2, the two value in equation 574 will be 0. However, the estimated beta 2 values depart from the hypothesized beta 2 value. This t value is greater than the larger than critical t values, so we reject null hypothesis. Yeah. We have here these regions because we have t value is t calculated t is 3.2. Yeah. Okay. We have critical value of t table from degree of freedom is 11 is 2.20, and we have calculated it 3.2. This means we reject null hypothesis. Okay, decision rule here. We reject as null if T absolute value is greater than T level. If we use two-tail here, the type of hypothesis here, two-tail, this is the rule here. Right tail, this is the rule, and the left tail, this is the rule. Any question?
Yes, sir.
Hmm.
I want to clear a doubt. Is the critical value the same as standard level of significance?
The critical value is used to compare the calculated value. If calculated value in absolute term is greater than critical value, this means we have the estimated parameters in the rejection area of null hypothesis. This means we reject null hypothesis. Without knowing the critical value, we cannot make any decisions whether we accept or we reject null hypothesis. Hypothesis is a standardized value to compare it with the calculated t value. You get it?
Yes, sir.
This is the same as we calculate for the t statistic. This is testing for sigma square significance level. We use this chi-square distributions. Suppose here we assume that the true value of sigma square is 0.6. Okay, we get before is sigma square head is a 0.8936. Our question is, what is the true value of sigma square? Is 0.6 is the sigma is the 0.6 the true value of sigma square? This is the summary of the chi-square test for the sigma square. Okay, if we assume sigma square is equal to true value, and then this is the null hypothesis. As alternative hypothesis, this is a rejection of null hypothesis. Hypothesis testing, some practical aspect. The meaning of accepting and rejecting a hypothesis. If on the basis of test significant, the t-test, we decided to accept the null hypothesis. All we are saying is that on the basis of simple evidence, we have no reasons to reject it. We are now not saying the null hypothesis is true beyond any doubt. Why? To answer that, return to our wage education example and assume that S null is beta 2 is equal to 0.7. Now the estimated value of slope is 0.7241 with the standard error of beta 2 is equal to 0.0701. So based on the formula we mentioned already, we get here the t calculated value. Calculated t value is at 0.343a, which is insignificant. We say that at 5% level, we accept null hypothesis. But now let us assume that the beta 2 is equal to 0.6. With the same calculation, we get 1.7703, which is also not significant. So that we can say that accept this null hypothesis. Which of these two null hypotheses is true? We do not know. Therefore, in accepting a null hypothesis, we should always be aware that another null hypothesis might be equally compatible with the data. It is therefore preferable to say that we may accept the null hypothesis rather than we do not accept or we accept it. Okay, because there is no guarantee that our model is the best model unless we can we use 99.9% significant level. Okay, we have rule of thumb here. If you get the t-value, for example, you have a 2.4 in the large samples, that means you can say that the null hypothesis is rejected because the largest value of t critical value is 1.96. Okay, if the number of degree of freedom is 20 or more and alpha level of significance is set at 5%, then null hypothesis beta 2 is 0 can be rejected if the t-value exceeded than 2 in absolute value. This is rule of thumb for the t statistics. Why use the absolute value? Because if we have two-sided testing, this means we use from negative part to positive part. So to compare it, it is more convenient to use absolute value of t, calculated t. Okay, well, I explained already for the p-value. Okay, p-value here I explained already. No need to explain again. Okay, we continue with analysis of variance. This is a table of ANOVA. Sometimes if you have this table, okay, you can see here source of variations due to regressions we have here. This sigma y hat square is equal to beta 2 hat times deviation of x variable. Degree of freedom is 1 here. Okay, and we divided this ESS with 1, we will get here mean sum of square. Due to residuals, we have here sigma square, okay, here mu square, hat square, minus n minus k divided by n minus k. N minus k, okay, if we divide it, this sigma square with n minus k, degree of freedom, we get here means sum of residual squares. Okay, if we add this ESS with RSS, we get total sum of square. Okay, here n minus 1, because we have here k minus 1 and here n minus k, we add n minus 2 plus k minus 1, we get n minus 1. Okay, this is a very powerful table. It's the table of ANOVA. F is a MSS of ESS here, divided by this one. We get F. This to F. This F calculated F value. There is no negative or in the F statistic. Only T distributions and normal distribution have negative variance. Okay, here, for example, sort of variation here, sum of square of regression, sum of square residual. Okay, here we have mean here, 95 of 0.4255 over 1 is the same value here. we get here 9.6928 divided by 11, we get here 0.8811. Okay, 95.4255 over 0.8811, we get 108 for the F calculated F values. We continue with the any question? No? Okay. This one is estimated value. We get applications regression to problem of predictions. This is the estimated results, the generated equation. 361 is equation. Okay, mean predictions. Okay, we have, for example, if we impose x is equal to 20, we insert the 20 here, we get here minus 0.0144 plus 724 times 20. We get here 14 point something. Okay, after having this one, we calculate the variance of prediction here. This is the formula 5, 10, 12, 20, 5, 10, 2. And then we use same standard t distributions. Okay, we insert the value from other equation to these equations, and then we can calculate this probability. Okay, the variant of y heads is 0.3826, and its standard error is 0.6185. With a 95% confidence interval, okay, for the expected value of y, this is a conditional expected value. We have here the value of 20 here. 20 times the estimated, the prediction for the 20 is, here we have, okay, we have value from 13 until 15. Thus given x0 is 100, in a repeated sampling, 95 of 100 interval like equation 5, 10, 5 will include the true mean value. The single best estimate of the true mean value is, of course, the point estimate is 14 point something. Because we get the estimated result is 14, then the interval from 13 to 15, this is we have the the best prediction value. Okay, no question. For normality, this is a normality test. Normality test is a one-off assumption in the classical linear regression model. We assume that residuals are normally distributed with zero mean and constant variance. So we use Jacques-Bera test here. Yeah, you can see this formula for Jacques-Bera. This is a Jacques-Bera statistic. Okay, we have this equation 5, 12, 1. Okay, for the normality test, we have here hypothesis testing. For normality assumption, null hypothesis is null. It's the residual normally is alternative hypothesis. This means the residual are not normally distributed. If the Jack-Vera statistic is greater than the critical value, okay, then we do not accept the null hypothesis. This means the residual are not normal. So in this case, we prefer to accept null hypothesis rather than to reject the null hypothesis. Okay, no any question? No problem? Oh, great.
Yeah.
Okay. I don't know whether you can understand or not. I hope. Okay. Okay. Now we estimate the equation here. For example, we use here our data. The important thing that's if you don't understand the class, the course, it is better to ask me. Okay. Don't be shy. It is the most tough subject in economics is econometric, and you have another class is time series. Is of brother of econometrics. Okay, next semester is time series analysis. Okay. Okay, I'm waiting for the data. This is very slow now. Okay, we use this table. You can obtain from Gujarati table, table 511. We have here smoking and mortality. Okay, we have sample here. We have around 20 sample. So first, we have to delete this, the rows from first until third rows. Okay, we delete it. Okay, and then we delete the fourth column. Okay, now we get only the data and variable names. That means we have 25 samples. Okay, we save this one. Okay. Smoking and death. Okay, now we use FUs again. I don't know whether you have the FUs or not. Did you get the FUs?
Yes, sir.
Okay, great.
Some have, but
Some is good, I think. Okay, you can borrow from your friend. Oh, where is the data? Smoking and death. Oh, already in my okay, now I show you the views here, and then we open for the data. Here the data. Okay, we take the data. Okay, did you see here? This
yes, sir,
views
yeah,
here.
yeah.
Huh?
Yes, sir. Yes, sir.
Okay. Okay, we have this variable mortality and smoking. You more you smoke, yeah, better to the most beautiful way of death. Okay. Okay. First, we choose the mortality for the first equation. This is dependent variables followed by independent variables. Don't forget to press the control and click the variables, and please choose equations here. We have here. We have estimated equation now. Mortality is a dependent variable. Smoking is independent variable. We have C here. C is a constant intercept for our equation. Because we estimate this OLS or the radius square, so we choose method of estimations is LS. So then click OK. We get here. Okay, we get here. This is a C. C is a constant slope. Constant intercept of the equation minus 2 point something. And we have a smoking value is 1.87532. Okay, we have this standard error for the beta 2. We call it this one beta 1. The smoking coefficient is beta 2. Standard of beta 1 is 23. Standard error of beta 2 is 0.22 something. And we have T statistic. What is the T statistic? This means 1.087532 divided by 0.220945, we get 4 point something. I explained already that our rule of thumb, if you get T statistic greater than 2, but here we have 4.92, and the p-value of the beta 2 is 0.001. That means less than 0.05, less than 5%. Based on this probability value of beta 2, we get this. This coefficient is statistically significant. Theoretically, state that if you smoke more, that's your probability to death is bigger. Okay, so the coefficient of smoking should be positive. Now we have positive estimated coefficient. This means this equation is this coefficient is statistically significant and theoretically significant. Okay, we have here R square. I explained already last week. Okay, adjusted R square. I will explain later for adjusted R square because this adjusted R square is better to explain in multiple regression model. This is standard error of regressions. Sum of square residual here. Okay, we have F statistic. Okay, we have mean dependent variable and so on. Okay. Okay, if you click here in the view and okay, if you residual, yeah, residual is to calculate, for example, normality test. This one normality. Okay, we have Jagbera 1.297 something. Now we have probability 0.5 is greater than 0.05. This means we accept, we do not reject null hypothesis. This means our data, our residuals are normally distributed. Okay, and then we have here representations. Yeah, mortality is for functions of smoking. And this is estimated values. Okay. Kemudian coefficient diagnostic. But if you want to make a residual, you can click proc, and then you can make residual series, make regressor group, make gradient group, and etc. Coefficient from equations. It's an object, you can choose this one. Okay, if you click here estimate, you can re-estimate again. It's in this option here. We calculate a confident covariant method with ordinary least square. Weighted no, which is selected here. Okay.
So I have a question about the residual testing.
Oh, residual testing. Normality, you mean?
Yeah, normality, yeah, because if I can remember, you said like if the Jagbera statistic is greater than the critical value, but I could not see the critical value there. I just saw, is it the same as the probability value?
Okay, I will show you this critical value for Jagbera. This is normality test. Okay, yeah. Probability value of Jagbera is 0.522729. You get it here?
Yeah, yeah.
Do you see?
Yeah.
Okay. This means that we cannot reject null hypothesis. Okay. This is a probability value, p-value of Jagbera. Okay.
Thank you.
Okay, you get it?
Yeah. So the other one is about the coefficient and the dependent variable. So if the coefficient like is as the better one, like if we have more dependent variables, then the more dependent variable we have, then we'll have beta 2, beta 3, beta 4. Or
yeah.
Like
yeah. Next class, I will explain you. Okay. This is a sequence subject. I cannot jump from one part to another part because you will get lost. Okay.
Yeah,
okay.
Yeah, okay.
No need to hurry up to get another subject because I have to explain for you step by step. Okay, actually I can explain you for non-linear regression model, but it's useless because your foundation is very unstable, you cannot understand the basic one. Okay, so I have to explain the first chapter one by one chapter, so you can understand from the beginning until the end. The objective of this class is to make sure that you can at least estimate your own data for your thesis in the last semester. Okay, we have two subjects for the numerical calculations. First is econometric, another one is time series analysis for the next semesters. So if you can understand these two subjects, I hope you can do by yourself for your thesis. No need to ask another people or other people to help you to estimate your thesis. Okay.
Yes, sir.
Okay.
Thank you.
Okay. So, actually, if we look at this chapter, actually, this one is a simple regression model. Okay. And then we continue with multiple regression model. Okay. Any other questions?
Also about the reviews, your adjusted R squared, what
Okay.
happens? Like, is it normal when it is less than 50%?
Okay, adjusted R square. Actually, I will explain this adjusted R square in the multiple regression model. Okay, I explained already. I cannot jump from part to the end part. Okay, because you will get lost. You cannot understand. Actually, adjusted R square is R square corrected by a degree of freedom. Okay, if you use R square without adjustment, this means if we increase the variable of the independent variables, the value of R square also increase. For example, okay, I will explain for you. For example, here, for example, we estimate the demand for ice cream. For example, the demand for ice cream. Then we make the equation for ice cream is a function of price of ice cream, okay, so, and income, family size, and expectation, etc. Okay, okay, here expectation. For example, we have only 4 variables. This means we have 5 cases here, and then we get R square here. For example, 0.9764, and then we run again this model. The demand for ice cream is the same variable, okay, in the beginning, and we add other variables such as the size of your shoes, okay, and the color of your clothes, and you get R square become, okay, 0.9912. The question is it possible to add the size of shoes and the color of clothes you are using have effect on the demand for ice cream? I don't think so, because we add irrelevant variable in our model, but the R square also increase because we do not make any adjustment for R square. So we use adjusted R square. Adjusted R square is more fair to evaluate or to assess the estimated equations. Do you understand it? Okay, if you add more independent variables, Even though the independent variable, the additional independent variables are not relevant to your model, the R square also increase. Okay, so it is not fair to use R square unless we make some corrections by using adjusted R square. Adjusted R square is R square corrected by degree of freedom. Okay, you get it?
Yeah.
Okay. No other questions?
Yes, sir. It's
Oh.
pertaining to that question. We want something clear. You know, we are told that if the R square is 50%, then it means that the research is a good one, something like that. But and the adjusted R square should also be above 50%. So in this case, if it's less than 50, that's the question. Like if the adjusted square, like from your e-views, we saw that it's 49, it's less than 50. So what does that indicate?
Okay. Okay. If you estimate, okay, estimate reference equation. For example, if you ask the respondent, which kind of car do you like? Usually, if you estimate this one, you will get R square around 0.3 until 0.5. Is it bad estimate? No. No, because there is no guarantee that if you have R square is high enough, this means your result is better than the lower R square. Because depend on your case. Usually, you use a qualitative model, you will get the lower R square. Okay, so don't worry about R square. The important thing is you have the estimated parameters is statistically significant, both in terms of theory and statistics, even though you have a lower R square. Okay.
Okay, sir.
Okay. No questions? No other questions?